Agenda today is first I'll give you like an overview of like what kind of like pipeline this is and like what problems we were having before with our Hive implementation, and why we like chose Spark in the first place, and our Spark implementation of this job, and finally we built some internal tools to help us optimize our job on Spark and do the migration, and finally some takeaways I want to share with you. So firstly, I will show you some results that I always like to brag. So several metrics we observed during our migration. So firstly, like CPU reservation time. This is not something like you typically see on like the when the job finishes, it prints like some line saying like this job took how many CPU years or how many CPU days. This is a slightly different metric where this means this much CPU was reserved by this job so that no other jobs can take it while this job is running. So this is actually the metric that matters by the end of the day, because this is the actual hardware resource you are like burning during this job's run. And for this metric, we have like 2 jobs migrated. This metric was like 3 to 5 times better from Hive to Spark. And there is another one. This is the one like typically exported and reported by our by the actual like job, saying how much time we spent in this job, and this is actually a percentage of like reservation time. It's always a like percentage. This thing CPU time is like I think 5 to 6 times better, and also another one which is like more organic. And also the thing that matters most to like our human beings and like our engineers and the one who's operating this pipeline is the latency, where it's from the time when this job starts to the time when the job finishes. But this metric is not like comparing the 2 like systems per se, because this metric depends largely on how much resource you dedicate to this job at a single time, and also and also how busy this cluster is by the time the job was running. But this is for like illustration purposes, and latency is I think 5 times better. But the takeaway is like it went from like 60 to 70 hours, which is like 2 days, 3 days, to like 10 to 15 hours, which is basically from unmanageable to manageable. Okay, so how did we do? What did we do to like get these results? So let's get started with like the more details of what's happening behind the scene. So firstly, we used to have like a Hive job, which looks like this. This is a slightly simplified version of it, and we have like 3 stages in this Hive job. Well, actually, it's like several hundred of Hive jobs, which is compiled into like a big pipeline, where logically it's like 3 stages. Firstly, we filter things based on. Okay. First, we filter things based on like the criteria we care about. This is a pipeline where we do. We build a ranking index out of like raw features. I don't know if you are like familiar with this specific problems. And so the idea is we collect all the like ranking data and then group by the user and target ID. After grouping by user and target ID, we get a feature set for each user and target pair. So in which there is like group by operation ongoing. And then after this group by operation, we pipe this output into a transformer, which is like a C++ binary, where we transform this group by result into a static RocksDB file where we serve like online. So the first stage is to filter and then group by. That's the first like 2 stages. And then the final stage is we do another round of group by to shard this data set into shards to be served in our online system. So the problem with this is, firstly, it's broken down into like hundreds of smaller jobs because Hive was not able to scale to this much like data. The input size is like 60 terabytes. That means that Hive is gonna have to shuffle like 60 to 100 terabytes of data like in just one job, which wasn't feasible at that time. And this is like our UI, which is like this. You can't actually read this. This is like you have to scroll like 12 screens of these to find, like, say one of the job failed at some day. You have to find it, and you cannot. And this is like very hard to manage. And yeah, these are like all the problems we had. Like this, the size of this job forced us to split the Hive implementation into hundreds of smaller jobs sharded by entity ID, which is like user ID in our case, and also like we have 2 checkpoints. Like the blue boxes here are actual like Hive tables where we, after each stage, we write the data back to a Hive table in case like this stage fails, and we can retry from a intermediary result. And it runs like very, very slow, which is like 60 plus hours. And right, so this was the problem we were having, and what can we do about this? So we were considering like options at Facebook that's available to us. Spark was one of the options, was starting to be one of the options like back a year and a half ago. Because firstly, like Spark was like, we are forming a Spark team in Facebook where like we are putting in like several dedicated engineers to work on Spark and work with the open source community. And also like internally in Hive, we have like our own fork of Hive, which is like in maintenance mode where fixes and reliability things is being patched onto it, but no dramatic like changes. And also we, according to some preliminary testing, we typically can get a better performance with the exact same query. Like Spark is similar to Hive as in it can run like the Hive QL, which is like the dialect of like Hive, like SQL when you write in Hive. And that those tests shows we can have a slightly better performance when we just run the exact same query. And also in Spark there's like more flexible API, where in Hive it's purely Hive QL. And in Spark there's you can choose from like Spark QL or Scala API, or you can mishmash them. Like some Spark QL and then some Scala and then go back to Spark QL, and you can do arbitrary things combining those two. That may or may not be useful in our case, but we will see later. And the problem is, of course, like it's never, the team was like kind of new, and it's never tested in our company, and we don't know how well it scales. So then we decided to try this thing, and we don't actually have like free manpower to do this. So we have this thing called hackathons at Facebook, where an engineer can spend a month on every like 18 months to work on something interesting, to work on something in another team. It has to be something in another team, and it can be something DAO, but you better work on something interesting. Right, so I took the chance of like this hackathon and started working on this since like Spark is like new to me, and also like the rest of Facebook was purely on Hive. There is like very few Spark pipelines. And this is like the largest Spark pipeline back then in Facebook, and I think one of the top pipelines in the industry. So firstly, what did we do like to move from Hive to Spark? Like the most naive approach is we just run the exact same Hive query on Spark as is. So yeah, so it's still the same query, And this chart is a little bit misleading. It's like faster, but actually this can only succeed on a smaller data set. I interpolate this number to come up with this graph. Like it can run on a smaller data set a little bit faster, but it fails on the entire data set. Problem so far is like, firstly, running the exact same query plan, the speed up is not significant due to like failures, because as we go to like several terabyte of input size, Spark just generates like a lot of out of memory, and the cluster is like restarting. I think firstly because there was bugs in Spark on handling shuffle and spilling, and also because we wasn't having too much experience with Spark, so like we were pushing it too hard. And also, according to our profiling, writing to HDFS is taking most of the time. And yeah, all these blue boxes is like taking majority of the time. So now we decided to, the lessons we learned, firstly, is to use the Spark QL, which is like a slightly different version of Hive QL, as much as possible. The reason being, Spark internally generates like the SQL queries into native code, which is like C++, and also it can avoid a lot of like virtual function calls when you use Spark QL. Like if you do like a plus 1 minus 10, it's gonna just be just one single like C++ statement, instead of like doing two virtual function calls, doing a plus 1 call and then do a minus 10 call. So use Spark QL as much as possible, because we tried to use Spark QL and also Scala, and we finally see like Spark QL is easier and also like faster with the same query. And also we see there's too much checkpointing going on because we profiled it. Checkpointing is good in the case where if your job fails like frequently, you do want to have some checkpoints to in case to that fails and you want to retry and stuff. But in this case, we're like spending most of our time on checkpointing. So then we did another try. So we actually tried like a lot of different approaches, and this is like I try to simplify this into like 3 stages. And then secondly, we remove this checkpointing. So as you see here, the checkpointing was to write to a HDFS a location, which is like Hive table. We changed that to be just writing to local disk, which is like faster, because to HDFS, there is like replication and everything. 3x replication, and sometimes it's cross network. So this time we get a slightly better speed up, still with like test set of data. We still cannot run on the full data set. And now the problem becomes like these two things, though it's written to local disk, but it's actually a shuffle. I'll talk about like shuffle later, but the takeaway is like shuffle is a very slow and expensive process, where it's moving data, the whole data set from a set of machines to another set of machines over network. And also there is still a lot of failures as we push our like data sets to like several terabytes. So here we seem to see that firstly, we need some like performance and reliability improvements in Spark. Otherwise, this cannot like work. And also, we are thinking, but as logically, the group bys we are doing in these 2 stages are like very simplistic ones, and they share a common prefix. Like we always group by user ID. So we were thinking, can we remove one shuffle? Because logically, it's just like one group by. So then we did another round of revamping this whole business logic into just one giant stage. As you can see the difference here, from 3 stages to just one. Actually two, because there is a shuffle in here. But like the input and output is like two Hive tables, and then there is one shuffle within this giant blob. This time we get a job with just one shuffle. Like we have to change the query a little bit to retain the same group by logic, but just one shuffle. And then the good part of this, like with fewer stages, Spark can generate more efficient code. Like I've said about like whole stage code generation, where the more complex calculation you have in your SQL, the more like virtual function calls you have in Hive, but not in Spark. In Spark is compiled into a single native function. So now the problem is like, firstly, it's still having like the out of memory issues and the scalability issues. And secondly, we are having too many mappers, which means our mappers are just keep submitting the job, and then it's completing like faster than we are submitting jobs. That means as long the time when you submit a job, the job like finishes right away. Like the cluster is idle, but the scheduler seems very, very busy. That means like we somehow need to tune the number of mappers we have. We want to have the mapper to run longer than our scheduling overhead, because most of the time is like spent in scheduling overhead. And we need to tune this, which like is like an easy thing to do. But we wasn't sure what's happening until like we had some like profiling tools. Yeah, so this is like the final version of this job, but there is like still a way to go, because it's still running like 2 times faster, I think, but it's like very unstable, and we have to like do some serious like work in Spark to help make this job stable and efficient. Yeah. So firstly, the thing we notice is like shuffling is like the easiest to fail thing in this job. I will just like recap, brush up everybody about what's shuffle. A shuffle is this stage where like when you do a group by, you try to like say you group by user ID and okay, in this case just user ID. When you're grouping by user ID, you wanna like, so all the mappers, the user ID is first scattered across all the mappers, like scattered across all the files on your storage. And then the mapper is scanning through each file individually and then trying to put the same user ID on the same reducer. As you see, like user ID 1 is always falling to reducer 0 and also user ID 11, reducer 0, and user ID 2 to another reducer. So this stage where these red arrows are is actually communicating over network to transport this data from mapper to reducer. This is slow, firstly because the mapper needs to sort or hash group by the keys on the left hand, and also reducer needs to do like merge sort and fetch over network on the right hand. And any cluster instability translates to stage retries. If, say, some mapper failed, or some mapper after finished, like, and then it goes into it goes like out of memory for some reason, then the reducer, because the reducer will very likely to talk to all the mappers out there. In that case, the reducer cannot proceed because maybe like just one mapper failed. So this is becoming a very, very painful and very slow process in our job. So what we did, we found like one thing, despite like all the memory and stuff, there was one very stupid thing happening. So this is what's happening before our optimization. Like the map task was firstly sorting, like in our case, like user ID. Sorting user ID and then put the user ID into buckets where each bucket is for one reducer. Like in this case, yeah. So the first bucket here is for reducer 0, and then the second bucket here is for reducer 1, and then to prepare for this data transportation. So for each shuffle partition we prepare for each reducer, we are doing one like file open, and then one file close for each reducer. And we have like 20K mappers, and also the number we have 20K reducers, and the number of mappers is like 100K. So totally, it's multiplying those two together is the number of file open and closes we do. It's like n squared. And then we actually realized we don't actually need to do those, like intermediary close and opens. We just need to do one open on the very start, and then just one close at the very end when we are writing to this file. So after this, we see 50% of speed up, which is basically going from n squared to like n. Well, and also because like shuffle is not the only thing we do here. So this is one of the fixes we made to open source, thanks to Sito in our like Spark team. And another thing is like we do like transform like extensively in our job, and that's like the part which also is likely to fail. As I just talked about, like shuffling. Shuffling means like you are fetching from network on the reducer side, and it's very likely on a large-scale cluster, the network can fail, and also the mapper can be like restarting or unresponsive for a short period of time. When such mapper is existent, you will very likely meet a fetch failure in the reducer side. And in our specific case, when we are doing transform, such fetch failure was from a subprocess of the Java process. So then it leads to a crash always before our fix. And then of course, the correct way to do this is to propagate this fetch failure back to the executor main thread, and which in this case help to in this case, the executor main thread is able to retry such fetch failures and then catch up on the mapper. This, I think, helped also a lot with our reliability. And there was numerous things we did, like here and there, like 7%, 10%, and 30% speed ups, thanks to our members in our Spark team. After which, this job is much, much more reliable than it used to be. And also, after these fixes, we also need to tune our still ongoing things. Is like we have to tune our cluster and job configuration to make sure like the slow things goes away. Like this is all happening as we optimize this and then continue with the profiling. Some highlights here is like shuffle service is constantly a bottleneck, as we just spoke, and it's really hard to like make it faster. So firstly, we have two little threads in our cluster, which sometimes will likely be true in your own setup too, because like Databricks, Spark, like the Spark's like mother company, I would say, is probably using a very different setup than you do in your own data warehouse. For example, like Databricks uses SSD, while like Facebook uses spinning disk. And also we tune our memory, and they use a much higher memory limit than like Facebook's machine has. And also always use like G1 GC, which is like a slightly like 20% or 10% faster than the default garbage collection setting. And also, the cluster configuration is mostly done by the cluster admin. And also, for each data engineer and the person who's writing these pipelines, they should be responsible for tuning the number of mapper and reducers, and number of like hosts, and the number of mapper and reducer per host. This is a bit puzzling to start with, because we don't know what are the right number of mapper and reducers we ourselves. So like after this, we built a tool to help you figure out how much mapper and reducer you should be needing. Like the criteria is basically each mapper should be running no more than like 20 minutes and no less than like 2 minutes. And also the mapper should be like processing roughly 2 gigs of data. And reducer, same thing. And also, yeah, the number of hosts in is just up to the cluster of yours. And this is like something each engineer have to do, and some of them can be automated, and some of them are already automated in our setup. And finally, I'm going to talk about some tools that we built that's super helpful during our migration. The first thing is, I think, like it cannot be more important, the profiling tool. All of the bottlenecks and the reliability things we spotted has to be firstly verified by this profiling tool. As you can see, the profiling tool is basically doing JSTACs, very simple approach, doing JSTACs on all of our hosts from time to time. And then we aggregate all those JSTAC into a central place, just like the thing like Max talked about. We have like central storage for such JSTACs, and then we have a visualization layer on top of this storage. In this case, we use the flame chart. In case you're not familiar with this layout of this graph goes from the bottom, or actually the top of the stack where the very first calling function, like this is like main function, and then goes down to the functions it's calling into. And then finally, you will see a rough idea of where you're spending time in this job. This is what time, by the way. So here, for example, we see we are reading from HDFS for like 6.5% of the time. This is like a HDFS read. So with this, you will likely constantly see like places where there's a huge block of like very slow functions, and it doesn't make sense. It's not doing the thing you're telling Spark to do. Like you're not doing your group by or your calculation or your like user-defined function. It's just doing some internal stuff. Those stuff might be the place where you want to take a look at. And also another very dumb thing we did, and also very useful thing we did, is like adding a button to do thread dump in Spark UI. Because we've always been seeing like the executor or the scheduler stuck for some reason, and we are like constantly doing JSTAC several times a day. And this is like a visual JSTAC we can navigate in. And it saves time. So I think that's what all we did for this migration, and the tools we built to help like future generations to do similar things. So some of the takeaways we've got from this is, firstly, try to use Spark SQL, and because firstly it's like the best performance in most cases, and also, yeah, and also we build like pure SQL tool chains. Like so in Facebook you don't have to really write like Scala, which I mean, in my opinion, a good language, but most people it has a very high learning curve. So we can write SQL like as extensive SQL. And also the migration candidates will possibly be those jobs with very high CPU usage and also doing a lot of shuffle, like large scale jobs. And you have to have your own profiling tool. Spark comes with a profiling tool, which is harder to use than you think, because it's profiling on a single machine, so you don't know the whole picture. But it kind of works if you don't have anything else. But better if you have some time, just try build your own profiling tool. So then it helps you tune the cluster, and also it helps you to tune the job configuration. Yeah, and yeah, typically migrating from like Hive to Spark isn't gonna magically just like work out of the box, though it's getting closer and closer. Like I was doing this a year ago, and by that time I spent a month on this, a month and a half on this, and together with a Spark expert, like who actually contributes to Spark open source community. But I think for now, if we want to do this again, it's gonna be like maybe just 1 week or 2. So Spark is getting better, and also like our Facebook deployment is getting more like reliable. So, and we've written all the technical details of what we've done in this blog post here, which you all can check out. Yeah, thanks. That's my talk. And any question?
Anyone? Thank you, Shoji. So we'll take questions now. We have 5-10 minutes for questions before the lunch break.
Hey, my name is Sahar. I've heard from a lot of speakers today, yesterday, in general, about Spark is great, and also it's really hard to debug and such a pain. So which is it? How can it be both?
I think it's, well, firstly, it's, I mean, the same thing applies to Hive, right? I don't know if anybody here can easily debug a Hive like failure if it's not a like typical thing you see like out of memory, those typical things. If you bump into something weird, then you are like very confusing also. And I think the strength of Spark is in its runtime, where running the same query on Spark versus Hive is almost always faster. Yeah. So I think the debugging thing, well, I think there's a constantly regression on how easy it is to debug Spark, because like constantly there is like people adding more confusing logs and then people fixing the logs. There's like constant battle on that front. So I think, but the people are aware that this is something they need to address. So like going forward, it should be getting better. Yeah.
Debugging distributed system is hard.
Yeah. Right.
Follow-up question?
Hey again. So I totally believe that Spark is better than Hive.
In some ways, I mean, there are cases the other way around.
Yeah. How do you decide when to use Spark versus using Presto?
Oh, that's a good question. So, yeah, Spark is claimed to be, Presto is like purely in memory so far. And Spark can use memory alongside disk. So it's like more adaptive. And also, typically when the data size goes to beyond like several terabytes, and also when you do shuffle. Shuffle means like you have to write things to disk to persist the hash and also transport over network. Those things Presto cannot do. As long as like data size is like several terabytes and you do group by and shuffle, then Presto won't scale.
Right. So to his question, so you're saying you use Presto for like mostly, but like analysts would use it for exploratory queries. That would be like a Presto use case, and then Hive is like it was used as an ETL tool and maybe also some like ad hoc processing. And maybe you wouldn't really use it for exploratory queries, right?
Sorry, what's that?
You wouldn't use it for exploratory queries and analysis.
Correct. Yeah, because Presto is much more responsive than Hive. Hive takes like 5 minutes to run just like limit one query like that, right?
So for your data size, like, would you say like 1% of that data is like used in Presto, and maybe 99% of it is not?
I think right now it's like 5% versus 95%.
Okay.
Because Presto also are working toward the model of like batch processing, but so far it's still in memory. But the scalability is getting much better than like a year ago. But still, it's mostly ad hoc queries.